Hi everybody, this discussion is a continuation to the first part that was on this chapter, chapter 18. For this one, I'm going to briefly touch upon a couple of points before we move on. And my intent is to get you guys to do example 18 or problem 18.67. It should not be hard to do. That is calculus problem. And then if you have difficulty with it, please let me know. Then we're going to discuss problem 1868 from this chapter and also 1878. Okay, this problem is a very important problem in the sense that it has data on it, and that's what physicists do on a regular basis. They deal with data. Okay, so one of the things that we discovered from the previous discussion is this one in here, PV equal to nRT, and we were able to connect this concept directly to we rewrote it basically in terms of Boltzmann constant, first of all, where big N now stands for the number of the particles actually, and we connected the concept of temperature to the kinetic energy of the individual molecules. Okay, so this is a molecule by itself, and this is how much kinetic energy it has, where this Kb is of the order of 10 to the negative 23 joules per Kelvin. Okay. So basically, this is how we came up with a conclusion. I mean, you can ask what is the entire energy of the system. It's easy to argue that it's the entire energy of the system. So this is the gas, not the molecule. All you have to do is just multiply this number by big N, which you can write it as lowercase n, which is the number of moles, times Avogadro's number times Kb, and Avogadro's number times Kb is just R. And that's basically how you can rewrite this entire expression for that. And I think we discovered that. One of the things that we did not discuss then, and that is the size of the molecules. We thought that they are point particles. Basically, they have no size, but the fact is they do have a finite size. And how much size that is, they are usually of several orders of atoms. That's what a molecule is. And the smallest one of them is actually one atom, which is of the size of an angstrom. And then when you have several of them, they could be several orders of an angstrom, which is probably a nanometer, okay, 10 to the negative 9 meters. And still, they are very, very small compared to the size of the entire volume in question in here, which is usually few liters at least that we're going to be talking about. And that is several fraction of cubic meter. It's still very, very large, okay, for practical purposes. So the approximation that we did is not bad. So what happened now when the molecule actually has a finite size, and now we have to take into account the fact that these molecules collide with one another? Well, the problem in this case, we have to make corrections to it, and one of the concepts that emerged from it is the mean free path. And what that is the following. So basically now I'm going to assume that the molecule has a finite size, and that size is of radius 2r. Okay, as long as this molecule does not encounter any other molecule, it's going to hit the wall. But if it finds a molecule, and that molecule at most is going to be sitting within another radius of 2r with it, so that's barely touching. Now, if it's less than that, that's going to collide with it. So the first approximation that I'm going to do is this molecule is moving with a velocity v, and after a certain amount of the time, delta t is going to travel this entire distance. And if it encounters on its way within a radius of 2r, because this distance is 2r, within a radius of 2r, another molecule is going to collide with it. So I will be able to find the rate of collisions. How much collisions do I have per unit time? Because I know how fast this molecule is moving. Basically, I can make an assumption based on statistics that we made last time. And based on that, we're going to find this area, of course, is going to be 4 pi r squared, because remember, it's 2r radius, so pi times the radius squared. And if I follow my analysis and assume that all of the other molecules are fixed still, and since they are uniformly distributed, these molecules, I'm going to use the symmetry again argument that the entire medium is isotropic. Then in this case, I have a number of molecules there, n, and the entire volume is v, so they're distributed uniformly with this quantity. This is the number of molecules per unit volume. And since this volume is simply v times delta t times the area, then in this case, I can see how many molecules it's going to encounter. All I have to do is just multiply this number by the density. From here, I'm going to argue that this is the rate at which this is going to happen, because this is the rate of the collisions, how many collisions that's going to happen. So if I move this one here, this is actually the rate of interest. I can invert this expression and find the time between collisions, okay? When the molecule is moving freely, and then after that it's going to collide with them. There is a problem with this argument in here, that I assume that all of the molecules are actually sitting still and only one of them is moving. We really have to take into account the fact that they're all moving in random motion. For that we need to use statistical mechanics, and that will bring a square root of 2 actually. That's also this argument. From here we can define the mean free path, and that is how far well, a molecule will go without colliding with any other molecules, and it's simply just the velocity times this time, which is just the invert of this expression in here, because you have to invert the entire expression, and the v will cancel the v, and the entire expression, this is the velocity, by the way. So this is the velocity, not the volume, and this is v, okay? So the entire expression now, if I write it down, it's going to be the volume divided by this 4 pi square root of 2 times r squared, times n in here. So it's just this expression inverted, and now I just multiplied it by the velocity v, so in other words bring the velocity back, and now I have a distance. So this is how far a molecule will go without collisions. I can express this volume in terms of the pressure, because I have actually v over n from this expression. So I can rewrite this expression in terms of macroscopic properties of the gas, and they are namely the temperature, this is just a constant Kb, Boltzmann constant, divided by 4 pi square root of 2 times r squared times the pressure. Okay, so this is measurable with the thermometer, this is measurable with the pressure gauge, and we can find how often these molecules can collide. Of course, if I increase the temperature, the path between collisions will increase. The distance between collisions will increase. The molecule can go a long time before colliding with other molecules, and if I decrease the pressure, the same thing can happen too. So that's an interesting thing to give me an idea into when can I expect phase transformations, when the gas will go from gas to other forms of matter. So this is a concept that we conclude with it, basically the discussion. Statistical mechanics has a lot of applications, and I mean, we can understand a lot based on it. Of course, classical statistical mechanics, that's what we're doing right now. It's Boltzmann. The statistical mechanics is just an approximation. Modern statistical mechanics involve two kinds of statistical mechanics, one due to Mr. Bose and Bose and Einstein, and the other one is Fermi and Dirac, and both of them deal with two kinds of particles, the so-called bosons and the so-called fermions. We'll talk about these types of particles when we get into quantum mechanics. Anyway, so let me get into problem 18.68, the one that I promised we'll do together. Okay, so problem 18.68 state the following. So I'm trusting that you guys should have no difficulty doing problem 67. If you do, please let me know. Okay. Anyway, so it says in here, so problem 1868, it says in here, what is the total random translational kinetic energy of 5 liters of hydrogen gas? And they give you the molar gas of the molar mass of this gas with the pressure, and which is just the atmospheric pressure, P equal to 1.01 times 10 to the power 5 Pascal, which is the unit in SI, and then a temperature of 300 Kelvin, which is room temperature. They give you a hint in here, use the procedure of problem 18.65. I'm not doing problem 1865, and I hope that you guys will have a chance to look at it on your own. Anyway, so they want us to find the total kinetic energy, Ke total, which is really what I was talking about earlier. So this total kinetic energy for the gas, total, I'm not talking about the individual molecules in here. So just 3/2 of nRT. Usually when I do R, it's for the total. When I do Kb, it's for the individual molecules in here. So when if I'm trying to find the root mean square of the velocity, the RMS, then I would be using this expression. Okay, so this will be 1/2 of the mass of the molecules times the root RMS squared, and from here cancel the halves, and from here you should be able to find the expression for the root mean square. We're not doing this, so there are a lot of problems that deal with this one, so I hope that you guys do that in the homework. Okay, anyway, so we use the KBT there, okay, but we're not doing that in this problem. So How am I going to find the, because what we're given in this problem, again, we really needed to list what we're given. We're given the volume V to be 5 liters, and a liter is 10 to the negative 3 cubic meters. Okay, so there are 1,000 liters in a cubic meter. So we're going to be using SI since everything was given. We're given also the molar mass of the hydrogen gas, and the molar mass for this one is 2.016 grams. So we better convert it to kilograms per mole. So if I know the number of moles, I know the mass. Okay, and they gave us also the temperature T is equal to 300 Kelvin, which is room temperature, and they want us to find this energy. I don't know what NR is. If I do, then I just multiply it by RT. But I know also PV equal to nRT. So I know this expression to be just PV. So all I have to do is, since I'm given P, the pressure, that's also another thing that was given to us. Okay, since I know the pressure, I know the temperature, I know the pressure, I know the volume, so we're just going to use that to find what the kinetic energy of the total gas is. So it's just going to be 3/2 of PV. I trust that you guys can finish this calculation, and that's item 1 that you're going to be focused on. So it's just 3 times 1.01 10 to the power 5, okay, times the volume, and the volume in this case is 2.016 times 10. No, I'm sorry. The volume is 5, I'm sorry, times 10 to the negative 3. Okay, the negative 3 cancels the power 5, and you do the algebra, you're going to find the answer in Joule. Please finish the calculation. So I want you to guys finish it. Please pay attention to the sig figs. Okay, I think this one has 3 sig figs, and I think so that's important to me. So that's part 1. Okay, so this is your job now, is to finish this part of the discussion, remember. Okay, part B, if the tank, if the tank containing gas is placed on a swift jet moving at 300 meters per second, by what percentage the total kinetic energy of the gas is increased? So basically think of it this way. So you have a gas now in a volume, okay? And we can find actually the RMS, the velocity of this particle, as they are moving randomly in here, because this is the whole thing. This is a random motion. So this kinetic energy is due to the random motion of this molecule. But now the whole thing is drifting with 300 meters per second with the jet. Okay, so I need to find the mass of this guy, which is the mass of the gas, times this velocity of the jet, squared of course, times 1/2. This will be the kinetic energy coming from the jet, contribution of the jet to the kinetic energy. Well, I don't know what the mass of the gas is, because the mass of the gas is just N times the molar mass. So the number of moles times the molar mass. But I'm going to use a symbol for the molar mass in this case as mu. Okay, just to not write this whole number together. So in this case, this is going to be 1/2 of N mu times the velocity of the jet squared. Well, I don't know what N is, but N is given by this expression, again, PV equal to nRT. So this is equal to 1/2 of PV over RT, and that is times the molar mass, that is just this number, times the velocity of the jet squared. It's very, very important when you do these problems to pay attention to the units, because it was given to you in gram per mole. So I need to convert that to a kilogram per mole. Did I do it right? This is a -3, I'm sorry. So hopefully that's good that you use symbolic manipulation. That way you don't have to. So this is 10 to the -3 because this is in grams, not in kilograms. Okay, that's to be terrible if the hydrogen is that heavy. Okay. Anyway, now, so we have this expression for that energy. Now, if I confront that expression with the kinetic energy due to the random motion that I just calculated in here, so we're in business. Remember, the kinetic energy was 3/2 of PV, so now the ratio of KE coming from the jet over that of KE coming from the random motion, coming from the heat, the internal of the normal motion. So it's going to just take this ratio. So I have a half in here of PV over RT times mu times the velocity of the jet squared divided by the expression that we found for this one, which is 3/2 times PV. PV and 1/2, PV and 1/2 cancel, and 3 will be fine in here, and we're in business. So this is equal to RT will come downstairs, of course, 3RT downstairs, and then I have mu in here, given by that number, times the velocity of the jet squared. Okay. There are some further simplifications if I plug in the numbers in here. The mu again is 2.016 times 10 to the negative 3 times the velocity of the jet. The velocity of the jet is 300 squared divided by 3 times 8.314 times 300. That's what I wanted to find, to see that 300 and 300 squared cancel. The 3 from the rest of the 300 cancel this 3, and I have again I have 100 left in here after all of these cancellations. That 100 cancel this one, and I'm left with a negative 1. So the answer is 0.2016 divided by 8.314. And if I do the math, and I did it with a calculator earlier, this is about 2.4%. Okay, it's going to be 0.024. Okay, multiplied by 100. So it's very minor corrections. Okay, correction. Now the question that was asked later on is, let's look at it again. C. Since the kinetic energy of the gas molecule is greater when it is on the jet, does this mean, so this is how much is going to increase, okay? So the kinetic energy initially was a number that you're supposed to find from the previous calculation. And this is how much it's going to go up by, 2.4%. So it's a small correction, but it's going to be nonetheless more, okay? Does this mean that the temperature of a gas has gone up? No, it should not go up because the temperature of the gas has to do with the random motion. This is now a uniform motion. The entire gas is drifting in one direction. So that should not increase its temperature, okay? If the entire gas is frozen, solid, and it's not doing the random motion, and it's drifting in one direction, that should not impact its temperature, okay? So that's the question for that. I'm going to stop here quickly to change cameras and or at least to do a screen recording for the second problem, because I want to show you how you're going to do that problem. Okay, I just pulled the GeoGebra in here for problem 18.78, and because 1878 involves actually a data, so I pulled GeoGebra. GeoGebra is a free software, and the reason why I pulled it in here so that to give you access to it so that you guys can use it. Anybody can use GeoGebra, so if you don't have Excel, there is no excuse. If you don't have anything in here that is really you can do. Excel can still do a lot of these things, but because we'll be using a lot of GeoGebra for simulations and other purposes, I put it in here. So what we're given in this case, we're given a set of points. Okay, basically what we're told, we have a sealed steel cylinder, or steel cylinder, yes, that is basically where we put in it a gas, and that gas basically we changed the container, we put it in different temperature regions, okay? Basically what we're going to be calling heat sinks later on. So we put it there, and then we measure the pressure because there is a gauge attached to that sealed container made out of steel. That way we'll be able to measure the pressure, and we're given a set of points. We're given 5 points in here. Okay, expect these types of problems in exams, so don't think that the data is really you're off the hook when it comes to that. It's really important actually when we do physics, because plotting data, interpreting data is a really critical point in here, and that's why we do a lot of labs. So this should also help you with the lab too. Okay, so the first thing I'm going to do is pull the spreadsheet from it. I'm going to go to the view, and from the view I'm going to pull the spreadsheet. Okay, it opens this window for me where I'm going to start putting data in here. So the first point of the data is negative 195.8, 195.8, and that gives me a pressure. There is a way, by the way, in GeoGebra on how to import a lot of data if you have a lot of data and you don't want to type them one by one, because then you would be prone to making mistakes. And then the other thing also is that it saves time. So you have 890, that's the second point. The third point in here that is of interest is 33.3 degrees Celsius. So this is the temperature now, and the pressure is in Pascal, 999 pascals. And then when it's 100 Celsius, that's when the water boils, we're looking at a pressure of 1214 Pascal. And then when we're given a pressure of temperature of a hot oven 232, that is 1635 Pascal, 1635 Pascal. So this is the data that we're given in here. So when we are in this view of the spreadsheet, we can actually pull the data. All you have to do is just pull it in here and go to the plotting and make a list of points. Okay, if I make a list of points, it doesn't matter, just give it a name, whatever name you would like to, and leave the default stuff in there. Okay, so it's going to name this list as L1. So let's say OK. And it's actually going to plot the points. So these points are the points corresponding to this data points in here. So negative 100, so that's the x-axis, the y-axis, then 0, 800. So it does all of these things for you. But where are my points? Let me make this one smaller here. The reason why is because the scale in here is very small compared to where they need to be. So this is, I need to probably, because I know they're all positive, so I need to move this. Here is the first point in here that appeared, that's point A from the GeoGebra, point B now in C and D. Okay, so this is basically more or less how these points look like. Okay, but that doesn't help me with the model that I have in here, because just plotted the 5 points, which I could have done them myself. Okay, assume that the gas is low enough for it's treated as an ideal gas, and ignore the coefficient of volume expansion for the steel. So basically, so at this point we're dealing with practical data. Okay, use the data in the table to calculate the value of absolute zero. So we need to know. So this x-axis is the pressure. The y-axis is the temperature. So we need to know when this graph is going to cross over, and it's going to be somewhere between negative 200 and negative 400 Kelvin. But we need to find that point. For that, we're going to come back to this one in here and model this data. So I'm going to come back into So we're going to select all of these points again. And we're going to go to the second tab in here, and we're going to do a regression analysis. Okay, two variable regression analysis, similar to what we do in Excel 2 when we do the trend line. So it gave me the regression right now. It just replotted basically the same points in here. I'm going to try a linear fit. A linear fit actually should work. Okay, so it gave me a linear fit, and in particular it gave me the function in here of y, which is the pressure, as a function of temperature. So we need this function in here because we're supposed to calculate when is the pressure going to be zero. Okay, all we have to do is just divide this number 888.8958. It gives you a lot of data in here when you're doing GeoGebra. Please do not report them. Stick to the sig figs, and I think there are 3 sig figs in this number in here. So 889 is the correct answer. Divided by 3.32, so the answer should be negative, because when we put y equal to 0, we should find what this thing is. So let's first of all do a trick in here, and that is copy to graphic view. Okay, so it copied the function, it copied the graph, it copied everything for us, so we really don't need this anymore. And actually we don't even need this spreadsheet anymore. So we have our graph in here. Okay, so this is probably what I could export as a result and I probably need to rescale my x-axis. But here is the answer. So the answer to the absolute zero, I'm going to write it T ABS, okay, is something equal to negative 889 divided by 3.23. Okay, so the answer to this one is negative 275.23, but remember we have only 3 sig figs, so it's negative 275 Kelvin, negative 75 degrees Celsius. So this answers the first question. Simple as that. Okay, the absolute temperature here, okay, based on this data. So that's easy enough. Now the second question in here is use the coefficient of volume expansion of steel, and the coefficient of volume expansion of steel, let me see where was that number, from the table, and give you the reference of what the table is and so on and so forth. So the coefficient of expansion of the steel is 3.6 times 10 to the negative 5. Okay, per degree Kelvin or per degree Celsius, it's the same thing. The point is, if the temperature increases by this margin, steel will expand by that much times the change in temperature. And it says in here, use the coefficient of volume expansion for steel from table 17.2, that is chapter 17, to calculate the percentage change in the volume of the cylinder between the lowest and the highest. So basically, I'm going to still use GeoGebra. I'm going to use, what is it called, beta? Yeah, beta is equal to, by the way, GeoGebra is case sensitive, so you have to really be careful with it too, okay? So it's 3.6 times, it's going to give me 0 when I'm done with this one because it's rounding the numbers. But believe me, when I do the math, it should give me a finite answer. So this is beta, okay? Do I have another beta in the problem in here? Oh, there is a built-in beta because the beta function. So I probably should not have used this one in here. So let me delete this entire entry and call it just B, okay? So B, lowercase b, because there is a case uppercase B if you guys see it in here, and that's the point B, that's part of the plot. So I'm going to use lowercase b equal to, because I don't want to do the index of 1 and so on and so forth. So it was 3.6 times, which is just the star, 10 to the negative 5, okay? So that's the coefficient of volume expansion for the thermal expansion for steel. So the question in here is use the coefficient of volume expansion for steel to calculate the percentage of change in volume of the cylinder between the lowest and the highest points in the table. Listen, the expression that we normally have for it is delta V is equal to beta times the initial volume V naught, and we're not given that, times the change in temperature. But now we're just finding the percentage change. So what we're finding really is the ratio of the change in volume over the volume itself. So that just should be beta T. So in this case, I'm going to call it change in V, okay, is equal to beta times T. And T is the T final minus T initial. And T final, I could look for the X component minus the Y component of these points. And here E and the X component of the point A, and do a complicated formula because if this number change later on, can this number change for me? But I'm going to just do the simple stuff in here, which is B times open parentheses, and the parentheses in this case is just 232 minus, so it's going to be plus 195.8. This point has 4 sig figs, but it doesn't matter. Okay, so that's the change in volume. As a matter of fact, I'm going to multiply this by 100 to make sure that I'm getting the answer in percentage. Okay, so it's 1.54%. Okay, so this is the percentage change in volume. Okay, 1.5% basically how much volume is, how much the volume of the steel has increased between the lowest temperature, which is negative 196 degrees Celsius, to the highest temperature, which is 232 degrees Celsius. Now, the question in here is, is it accurate to ignore the volume change of the cylinder? Because we're assuming that this is an isochoric process, a process where the volume does not change. The only things that matter in this case are the pressure and the temperature. Those are the things that change. The volume actually changes, and it changes by 1.5% overall from the lowest temperature to the highest temperature. Okay? So, if we are using this device to measure changes in temperature that are a lot smaller than this should not really matter that much. The pressure reading and all of this reading, the analysis is accurate. But if the temperature range is that much between those is large, like this range, the temperature will matter. In this case, the measurements will matter. So as long as the temperature changes are not large, so that's basically the discussion that you're going to say, you're good. Okay? So this is in a nutshell problem 17.8. I really wanted to have you guys have an understanding of how this tool works. You can do a lot with it. You can actually solve differential equations with it. But I'm doing this so that you guys can have this problem 17. Again, we could have done it a lot easier. Problem 78. We could have done it a lot easier with Excel, or maybe different with Excel. I shouldn't say easier. But this one has a lot of things in it too that I wanted to bring to your attention. It gives the answer, it gives everything, and you could have done it manually too. Here is the answer to part A, negative 275 degrees Celsius for the absolute temperature, and the change in volume is 1.5%. And I could write in here these answers if I'd like to. Thank you. So I hope that you picked up the discussion points for the entire chapter. So where is the pause?